All right, thanks so much, Ryan. Can everyone hear me? So I'm going to ask Ryan a whole bunch of the questions that you guys have come up with throughout Ryan's talk. So it was an awesome talk. Thanks so much, Ryan. And there were so many questions as well. So I think what a lot of people were asking was, have you found any exoplanets that look like Earth?
Yeah, that's a very good question. So that's one of the big topics which people using TESS want to find out. So if I run back a few slides, all the way back to here, if you remember these three planets here, the first one is a little bit smaller than the Earth. The second one is bigger than the Earth, and we think possibly something like Neptune. And the third one is about Earth size. So since it's Earth sized and in the habitable zone of the star, it's very interesting for astronomers to go and look at it to try and understand if there could be an atmosphere there or even life on this planet. But at the moment, I think there's only around 10 or so planets that we know of that are about the same size as Earth.
Awesome. So that leads us to the very next question, which is, are there any signs of life on these exoplanets?
No signs of life yet. TESS isn't a very good instrument to look for signs of life. It can find planets well, but it's not very useful for detecting if there's any life there. To do that, there are two ways. You could use big telescopes like the James Webb Space Telescope, which is supposed to be launched in the next few years to try and find out what the atmosphere of these planets are like. And you can look for things like oxygen and methane in these atmospheres, which indicate life. Or you could look with radio telescopes to try and find radio signals. So if there's civilization, we might be able to detect radio signals from it.
So we can't really see life. We have to look for kind of the byproducts of life and things that life may produce.
That's exactly right.
Cool. So another question that came up a fair bit was, how big are exocomets?
Yeah, that's a very good question. So you can tell the size of objects based off their tails, or sorry, based off how deep these depths, or how deep these light curves drop when something goes in front of it. So in this case, it's dropping by something like 2 millimag, which is a strange unit. What that means is it's probably around about the size of an Earth-like object, between an Earth-like object and a Jupiter-sized object passing in front of the star. So these comets have absolutely enormous tails, which is really cool and can provide us with some information about how planets actually form in these young stellar systems.
Wow, so cool. So I thought a very cool question, and I think it was from Zaki, if I remember, was, are there any exoplanets orbiting neutron stars? So maybe you want to describe to us what a neutron star is first.
Yeah, that's a very good question. So a neutron star is caused by something blowing up. So in this case, we'll say a supernova, a core collapse supernova. When it blows up, the core of that star will collapse down and form something called a neutron star. So at the center of this big expanding nebula, we have a neutron star spinning around, and they emit big beams of radio light that we can detect with radio telescopes. So the first exoplanet was actually discovered around a neutron star.
Wow.
So neutron stars emit big beams of radio jets out their poles, and by measuring the the beams, as they pass in front of us, like a lighthouse might spin its light, you can time the spin of a neutron star very accurately. And one of these neutron stars, they found its spin was not quite right. And the only way to account for it was to put a planet orbiting the neutron star. So the first ever, that was in 1994, I believe, was when the first exoplanet was confirmed. But it's worth noting that this planet would probably have formed after the star actually blew up, because otherwise a supernova would have destroyed that planet. So with every supernova, there's a few planets that get destroyed with it.
Cool. So people have also asked, do exoplanets have rings like the ones that we see in Saturn and Neptune?
Exactly which one it was, but there have been exoplanets that have been detected with rings around them. You can see the imprint of the rings in the light curve. So as we showed a few times, sometimes, if I go all the way back, so this is what a nice exoplanet transit should look like. But if it had big rings around it, you'd expect some changes to happen around the edges of this light curve. So there have been a few that have been detected with rings around them.
Yeah, so I think just pausing on this diagram for a second, people have been asking so how does the size of these light curves, the size of the dip, how does that relate to like the planetary mass and other properties of the planet?
Yeah, that's a good question. So the size of this dip is determined by how big the planet is compared to how big the star is. So if the planet is 100 times smaller than the star, it'll only block a tiny amount of the light coming from the star. So you'd expect a very small dip in brightness. But if it's, say, half the size of the star, then you'd expect an enormous amount of the light being blocked, which will cause an enormous dip. So the depth of this dip tells us the relative size between the star and the planet. And then we look to see multiple dips, so multiple orbits around the star, to tell us how far away the planet is from the star. And with that, you can calculate the orbital period of the star and a few different things like its density and a whole bunch of other fun things.
Awesome. Okay, so it seems like there's lots of information that can be extracted from the curves themselves. So we had some other questions about why the camera of TESS is so strangely shaped. I think you showed it had kind of these like 4 different camera parts, and they were all kind of like not quite, circles. They look more like jelly beans kind of thing fitting into the TESS jigsaw.
Yeah.
So why?
Yeah, that's exactly right. So the camera for TESS needed to be aligned so that they covered a large patch of sky. So if we go back to the sky, different sections of the sky, and to make sure all those cameras could actually line up correctly, they needed to be jigsawed together kind of in this fashion. So they look pretty weird. Each camera will have a slightly different shape to it. So they're all custom built for this telescope.
Oh, okay. So how long is the TESS mission? So how long will it actually be in space?
That's so TESS will probably never come down. It's been in the orbit of Earth for 2 years now, and the state of stability of TESS's orbit is incredibly high. So you could keep TESS in that very same orbit for, I think, hundreds of thousands of years without even using the fuel it has on board. So it's gonna be in space for forever, pretty much. So it's just a question of how long can its instruments survive and function, and how long will there be money to pay for people to work on this mission?
Oh, cool. Okay, so I think Declan has asked this question a few times, so I'll tell you it right now. If planets not circling our sun are exoplanets, then if there were life on other planets, would we be an exoplanet to them?
Yeah, that's exactly right. So if you were to live on a planet on, say, orbiting Alpha Centauri, then you would see the sun sitting in the sky, and you could build a telescope like we have with Kepler and TESS and point them at the patch of sky that you would find our sun in, and you could see dips in our sun's brightness, which would correspond to planets like Jupiter, Saturn, and maybe, if you're sensitive enough, the Earth going around. So there could be aliens out there at this very moment searching for other planets and looking for life like we're doing. But sadly, we've found no evidence of those aliens so far.
We'll keep searching, I'm sure.
Yeah, got to search to see.
So how far away is the closest supernova to Earth?
Yeah, so the closest, well, the one which everyone's been looking at recently, hoping it's going to blow up, is Betelgeuse. And that's may or may not blow up in the next 10 or so thousand years. There have been other supernova inside of our galaxy a few hundred years ago, or sorry, a few thousand years ago, which would be 1,000 or so light years away from us. But in general, we find supernova in distant galaxies. So these are galaxies that are millions to billions of light years away from us. So fortunately, that means we won't get blasted away by these supernova. But unfortunately, it means that the information that we can collect on these supernovas is kind of limited.
I see. So another question that is popping up in the chat a lot is, can we artificially make a supernova? So can we somehow explode a star artificially?
Right. So there's one area of astronomy which is very important, and James knows an awful lot about it, and it's using computers to model physical processes in the universe. So we can't physically blow up a star somewhere in the sky, but what we can do is put the laws of physics that we know into a computer simulation and see what needs to happen for a star to blow up. And that's actually a very complicated job that many astronomers around the world have been working on for a long time, is how do you actually blow up a star? It may seem simple, like you just make a star collapse on itself and explodes, but the exact physical processes behind that requires a lot of detailed information.
Yeah, it's very hard. There's many scales you have to resolve properly too, which is the hardest thing. Astrophysics happens on such large scales, but the very small scales are important as well. So that's very hard for a computer. People have been asking about hypernovas. What is a hypernova?
So I guess an easy way to think of a hypernova is it's just an extremely bright supernova. So hypernova are sometimes also called superluminous supernova. And they're supernovae that are maybe 10 or 100 times brighter than what you would expect them to be. And there are a few things that could power these hypernova. One thing is if you form a neutron star at the center of a supernova, and it happens that this neutron star has a very strong magnetic field, it can push a bunch of material out at very high speeds and create very bright interactions between atoms, and that can power hypernova. One which you might see in the news lately is the brightest supernova ever discovered has been, I've seen that article traveling around, where the researchers think that they've found evidence for matter-antimatter annihilation at the center of a big star. We don't know for certain that this is the case. It could also be a very magnetic neutron star powering it. But these very big stars have very interesting ways that they blow up. So it's cool to find them. And they're pretty rare as well. So when we do find them, there's a lot of interest in it.
Wow. So a lot of people are also asking, what has been the closest supernova to the Earth?
That's a good question. I don't know the exact one off the top of my head,
Was
but
it the
there's
one in?
evidence.
Yeah.
There's evidence that we've had supernova dust fall on the Earth over the past tens of millions of years. Some people, I'm not sure how truthful this is, but there have been some claims that the Earth passing through supernova debris, something like 50 million years ago, might have caused forest fires around the world. So there's some tenuous evidence for supernova interacting with the Earth in the past, but the closest ones we know of are still thousands of light years away.
So there's a lot of questions about black holes, so I might ask you some of those now. So moving on from supernova. So black holes tearing up stars. This is kind of what you were describing in the last part of your talk. So how do we actually know when it happens?
Yeah, so that's a very good question. So when you're looking for supernova or things like black holes tearing stuff apart, you have no idea where or when it's going to happen. You just need to look at a whole bunch of the sky and hope you get lucky. And the way you find it out is if you look at the brightness over time of a patch of sky and you see it follows a characteristic shape, so it gets bright over the course of 30 days or something, then that's a good indication that you've spotted a tidal disruption event. You can take spectra of these objects, which is measuring all the different colors that come from it, and doing that can also tell you some information about what's actually going on. So there are lots of different tools that we have, but the primary tool we have is just looking at how the object gets bright and dims over the course of time.
Okay, that makes sense. Is a white hole a thing? So some people have been asking about white holes. Do white holes exist?
Theoretically, they're possible, maybe. So that's a pretty bad answer, but it's an answer that's fitting of the amount of information we have on these things. So black holes, as we're all familiar with, are heavy objects in space, and stuff that falls into them can never get out of them. White holes are the theoretical opposite of a black hole. They're just a point in space which emits particles. So they just blast out a whole bunch of stuff into space. These have not been found yet. There have been lots of people who have thought about ways we could find white holes, but we've found none so far. And at the moment, they still look like a theoretical idea.
Cool. So how many black holes are there in the universe? This is a kind of a very hard question.
Yeah, the only way I can answer this is just hand wave and say billions and billions.
Yeah,
so
billions and billions.
In the center of every galaxy, there should be a supermassive black hole, and within a galaxy, there should be numerous black holes just kind of hanging out. So since there are trillions of galaxies in the observable universe, then there's at least trillions of black holes in the observable universe.
Cool. So can black holes move, or are they just fixed in space?
So black holes follow the same laws of physics that everything else does, in particular gravity. So just like the Earth orbits around the sun and the sun orbits around the center of the galaxy, a black hole will move through space as gravity will tell it to. So small black holes will orbit the center of our galaxy, and the big black hole at the center of our galaxy is moving around on its way to collide with another very big black hole at the center of another galaxy.
Oh, I'm seeing so many interesting questions in the chat. Just how did black holes form? How do you know when the black hole happens? Can you go into a black hole and go out the other side? So maybe we should try to answer the, how do you go, can you go in a black hole and go out the other side?
Yeah, so imagine you're in a spaceship and you're headed towards a black hole. Do you think you would survive better than what a star would? Put your answer in the chat. Let's see. Let's take a little poll.
So remember,
I'm
everyone,
seeing some
stars
no's
get
there.
torn apart from black holes because the gravity is so strong. It pulls the parts of the
there's a good
star that are
answer.
closest to
I
the
see
black hole.
someone that says you'd get spaghettified. That's exactly right. So
Cool.
you'd get
That's
torn into a big
very,
long piece of spaghetti, and that's it.
very Neil deGrasse Tyson kind of answer. Spaghettification.
Yeah, it's such a strange word that's actually scientific.
Awesome. So there's some just random other questions that maybe we can try to answer in a minute or so. So how old is the universe? Someone asked.
That's a good question. So the universe is about 13.7 billion years old. That is from the Big Bang to now. If you want to ask the question of what happened before the Big Bang, that's a question myself nor anyone else can answer. So there you go.
Well, that's excellent. I think it's a nice way to finish this talk on the age of the universe. The oldest thing in the universe is the universe itself.